So chapter 4 is somewhat linear. Get it? Ha ha ha. In the fact that 4-1 like snowballs into 4-2 and that snowballs into 4-3. So 4-1, we're introduced to scatter diagrams and just seeing does a relationship exist or not. And then that's all we do. We're like, yeah, a linear relationship exists. Great, you know. But 4-2 says, well, now that we know a linear relationship exists, what line best describes that data? And this is what's crazy is you wonder where all these lines come from in your college algebra classes or whatever it may be. They are doing exactly this. So they're collecting data and they're building their equations based off of the data they find, okay? So we are going to be visiting that line, that y equals mx plus b in this class, but what's going to be different is our data points don't all fall perfectly on the line. We're kind of off by a little bit. So it says if we have two variables x and y, we often can model them with a line, and you usually draw a line through the scatter diagram. We want to find the line that best describes the data, meaning how close can we get to every point? Can we minimize our error? These are all different ways to describe data. Y equals mx plus b, I think, is the most common one. But in your calculator, for some reason, they use a instead of m, okay? So we'll use y equals ax plus b, and we're going to go from there. So what I want to do is show you what the point of section 4.2 is. I know it's usually like, why are we doing this? So guys, this is just back to our data that we had for the golf club, okay? Back in the day, you guys learned how to make equations of lines. Does this look familiar? So if you had 2 points, you could find the slope between 2 points using m equals y2 minus y1 over x2 minus x1. You get your slope, and then you could put it in for m and b, blah, blah, blah. So you could come up with an equation of a line. So that's what they did. They picked this very first point and this very last point and said, oh, here's a line that describes the data. In general, guys, that's a pretty good line, but the thing is, there's a pretty gap between this point and that line, this point and this line. So the question is, do we have to really go through 2 points, or can we just kind of skim through all of them and be closer? And that's our whole goal, okay? So the first thing we want to realize is when we have a line, we're not going to go through every point. There's going to be error, and that's called a residual, okay? So I want to show you that. This gap between the point and the line, that gap, how far you're off, is called the residual. And how you find the residual is take your observed, the actual data point y value, minus your predicted, what you would get if you put it in the line. So let's just do that real quick. So that's a visual of what we're doing, all right? So objective 1, finding the least squares regression line. We might worry about that on Monday. But what we want to talk about is if we have this line, it's not going to be perfect, okay? So we're going to have a little bit of an error. That's called a residual. Guys, there's going to be a lot of similar words like R or correlation coefficient and residual. There's a bunch of R's and C's and stuff going around. So the formula for the residual in stats terms is your observed minus your predicted. If you want to put observed, you put the Y from data. The observed value is what actually happened. It's your Y value from your data. How far did that golf club or ball, not the club, hopefully he's not throwing his club. How far did the golf ball actually go? What we recorded, that's your Y. Your observed, guys, they actually is what you get from plugging it into the equation. So the Y from equation. And that's usually denoted Y hat. Okay, we haven't learned about him yet. We'll learn about him on Monday. He's just a party animal with a little party hat on, okay? But what we're going to do is we're going to have actual Y values from what happened. We're going to have an equation so we actually can plug in how fast we swung the golf club and figure out what that was supposed to be. So here's just a general one. So back to our golf club example. Say someone's really cocky and says, hey, I think the best line to describe this data is y equals 2.8x minus 22.5. I think if you plug in your x, how fast you swing your club, you should get your y, how far your ball should go. Okay? Okay, let's try it, all right? So we're going to find, it says use the equation to predict the distance a golf ball will travel when the club speed's 103 miles per hour. Predict means plug in, okay? So what do we have? We have this line y. We have 2.8 times x, but x was our club speed. And what was our club speed in this problem? 103. minus 22.5. You guys see what I did there? I'm just taking my equation, 2.8x minus 22.5, where x is how fast we swung our club. So in A, they wanted to know how far should my ball go when I swing my club 103 miles per hour, okay? So you put it in there, and you get a rough idea of how far the golf ball is supposed to go. What did you guys get to 1 decimal place? 265.9. And then y is the distance that it traveled, so that was measured in yards. This is our predicted value. Meaning, if Mr. Cocky thinks his line's so great, that all these predicted values should be pretty darn close to how far the actual ball went. All right? So anytime you guys see the word predict means plug in. Predict means plug in. Plug something in for your x. In this case, we plugged in our golf club speed. All right. B, what was the actual? Actual is your observed. What was the actual distance that the ball went when the speed was 103 miles per hour? So if you flip your page to, is it just on the back of here? Yeah. Is it just on page 4? Yep. So when it went 103 miles per hour, guys, the distance was 274, okay? So that was 274 yards. Are they perfect? No. Will they always be perfect? No. But we want them as close as possible. We want a really good equation so when Molly, the bad golfer, goes, she has an idea of how far her ball is going to go based on her 70 mile per hour club speed or whatever it may be, okay? So the last thing is the residual. The residual is just the error, the gap. How far off are these two values, okay? So the residual, I'm going to write it out. It's observed minus predicted. And I like to write that formula because the more we write that formula, the more comfortable we get with which one's the observed, which one's the predicted. Remember on these exams, I will give you the formula sheet. You won't use a single formula from chapter 4, except for probably this one, okay? Because R squared, all that stuff comes on your calculator, but residual you might have to look at. All right, so what was the observed value? How far did our ball actually go? 274 yards. Minus the predicted value. Remember, the predicted value is what you get when you plugged it in. What was that, 265.9? So what is the residual in this case? Is it 8.1 yards? Does that look right? So what does that mean? It means this equation wasn't horrible, but we were off by 8 yards, you know, and at a certain point, 8 yards starts to be a decent distance. All right? So let's go ahead and turn the page and ask ourselves, well, Mr. Cocky, who thought his line was so great, how do we find a better line? No, not better. How do we find the best line? And that's what we see at the top of page 6. All right? It's really wordy, okay? So it says, if we're going to find the best possible line to model our relationship, the way to do that is minimize the residuals. Because remember, the residuals was the gap. We want all those to be as small as possible. So that's why it's called the least squares regression line, okay? It's the one that minimizes the sum of the squared residuals, okay? Minimizes the sum of the squared residuals. There's a lot of words going on. Minimize, because we want to make it the smallest. Residuals, because it's the errors, all right? So we want to minimize the residuals. But why do they have to be squared? Because sometimes your residuals will be high and sometimes they'll be negative, okay? So if we start adding them all up, they start canceling each other out. So it's kind of like the standard deviation where we need to square them so the negatives are positive and so forth. What you want to take away from this, guys, is that the least squares regression line is y hat equals ax plus b. That's our equation, y hat. Y hat equals ax plus b. And really, guys, I think this sentence right here, right behind y hat, says it in layman's terms the best. This line is as close as possible to each of the data values when it's all said and done, okay? We might not hit a single data value. We might not go through a single point, but we're trying to squeeze by and get as close to all those points as possible, okay? So what we want to do is, let's find it using our calculator. Yay, guess what you already have? No, you don't, because I was mean and made you do a worksheet in between. Shoot, okay. So we're going to use our same golf data from 4.1, and we want to find the least squares regression line. What we need to do is we need to go back to our data on 4. I apologize that I made you do that worksheet in between. Sorry. All right. Go ahead. Let's enter our data back into list 1. So put your golf club speeds in list 1. Put your distances in list 2. And then we're going to go to StatCalc 4. But this time, instead of wanting R, our correlation coefficient, we're going to want the A and the B, and we're going to make an equation, okay? So I'm going to go to StatCalc 4. And it didn't tell us what to round to. My math lab will say round to the nearest 10th or round to the nearest 100th. Let's round, what do I round to? Let's make sure I'm rounding right. Let's round to just the nearest 10th. So what we have to do is we have to build this line. What is always in your line? X, okay? So don't forget X. X is that variable. But it will tell you A and it will tell you B, okay? If B is negative, my math lab's really weird. I don't like how it does it, but this is how it has it. It'll have y hat equals, and then it will have a blank x plus blank. And you have to fill in the A, the slope, and B, the y-intercept. So in this one, we would put 3.2, and I think it has parentheses like this, and we put negative 55.8. Is that what you guys got? Yeah. Okay. That's how my math lab would have you fill it in. Does everybody see where the 3.2 came from and where the negative 55.8 comes from? I don't like this. Why? Because from a very young age, when you first introduced equations, you know a plus minus is not supposed to be by each other, right? So what will I look for on my worksheets and on the test? Y hat equals 3.2x minus 55.8. I will accept either one because my math lab pushes you kind of towards that, to me, incorrect way. But I preferred this one. Are there any questions of where the 3.2 came from or the negative 55.8? Just straight from your calculator. Don't forget the x. The x is that variable for the club speed, okay? So now, part B, we're going to do exactly what we did on the last page. We're going to predict the distance the ball goes when we have an x of 103, but now we have a new line, okay? Supposedly we have the best line. So we're going to use this equation right here, but n for x, we're going to plug the golf speed of 103. We want to see how far our golf ball is actually supposed to go. So remember, predict means plug in. So we're going to have y hat equals 3.2 times x, or our club speed of 103, minus 55.8. So they're going to give you, or you're going to find an equation, but after you find that equation, they typically have you use it to predict. So you just do the math like normal. 3.2 times 103 minus 55.8 in your calculator. And the whole hope is that we're going to get a value better than that 269 or whatever, 265.9. We hope that we're closer to 274. So when you do this, I got 273.8 yards. Does that look right? So don't you guys agree that that's closer to the 274 than that 265.9 that we got on the front page, the supposed best line that this guy said? So remember, residual is always going to be observed minus predicted. Your observed value is always from your actual data. Okay, how far did the ball go when it was hit at 103 miles per hour? You just jump back to here. It went 274 yards. But how far did we just predict it to go? The 273.8. So that's just a difference of 0.2 yards. And that's the whole point of the least squares regression line. You can be as cocky as you want and say that you have the best line, and it might give you a decent estimate, but this line will always get you as close to the real thing as possible. Notice 0.2 yards is a lot better than 8.1 yards over here. So this one, based on this just random line, that was just a random line that somebody threw at us, gave us a residual of 8.1. But here, when we use our least squares regression, the best line, we got a really small residual there. Okay? The last question, guys, is D, is the observed distance from a ball hit at 103 miles per hour above average or below average among all balls hit at 103? All right, so the observed distance is how far it actually went. How far did it actually go? 274. How far was it predicted to go? 273. So was it above or below? What? Above, okay? Our ball of 274 yards went further than it was supposed to go, 273.8. How you can tell is based on your residual. If your residual is positive, you did better than expected. If your residual is negative, that means you were lower, all right? So it's above average. Positive residual. Basically, our ball went 0.2 yards further than it was supposed to go. Say when I hit it and mine only went like 100 yards, my residual would be a negative 173, right? So I was 173 yards shorter than what it was supposed to go. So this is like the supposed average based on all of his data points. We kind of found the average distance it should go at 103 miles per hour. But what actually happened was 274. They won't match. If you have if you have a residual of 0, it means they match perfectly. But they won't, okay? It'll either be positive because you did a little bit better, or it'll be negative because you did a little bit worse.